All right. It's 3:10, so we can start. It's my pleasure to introduce Frits Paerels. Frits and I are both Dutch, as is Martin. I've lived in New York for 4 years, pretty much visiting his department weekly, but we never met due to COVID. Yeah. Then I finally moved to Toronto, went back to New York to visit, and then we actually, by coincidence, we met. So I thought, why not invite him to Toronto? Frits did his PhD in Utrecht in the Netherlands. He was then a researcher, a postdoc at Berkeley. Went back to the Netherlands for a little bit until he ended up at Columbia as a professor, where he still is. He's an expert in many things. He knows everything about instruments. He knows everything about observations, and I found out he impressed me by just citing the Hamiltonian and explaining to me how the quadratic Zeeman effect works out of the top of his head. So he also knows everything about theory. So he seems the perfect speaker for us. He will be talking about neutron stars, which can only be interesting, right? They're the most interesting objects in the universe. Without further ado, Frits, take it away.
Thank you. So now you... So now Bart has, of course, raised your expectations to impossible heights. So thank you very much for inviting me. It's a great honor to be here. I'm really excited, and you are going to be the first professional audience that I'm going to be showing some of this work to. So if you end up laughing me out of the room, I'll probably pack it up and resign. So don't spare me your criticism, please. So I chose a title for the talk. I'll be talking about neutron stars. And I think we've recently acquired data that allows us to do measurements concerning the fundamental properties of neutron stars that we've been trying to do for several decades. And I think we now have the material to really do them. So I'll try to explain to you a little bit about neutron stars and why they're interesting and how this is related to fundamental properties of matter, how astronomers have struggled to say anything definite, quantitative about the properties of neutron stars for 50, 60, 70 years now, and what progress we've actually made recently in addressing some of those questions. And at the end, I'll tell you about the work I've been doing. So you can see here a picture that's an X-ray image of the supernova remnant Puppis A. So we'll review this in a few seconds, but you remember, right? Supernova explosions, it's kaboom. A lot of very hot interstellar gas that stays around for maybe 100,000 years, glows brightly in X-ray. So this is the supernova remnant Puppis A, piece of it. And over here, that little dot, if you can see it, is the neutron star, right? That's the remnant of the thing that exploded, the stellar core that exploded. The neutron star is about 3,000 to 4,000 years old, we estimate. It is a thermal emitter. It looks like it emits a thermal, roughly a black body-like spectrum with a temperature that's a few million degrees, 4 million degrees Kelvin at the surface. And it's a weakly magnetized star. So my colleagues at Columbia found that it was found that it is slightly periodically variable, a very low amplitude, with a period of 112 milliseconds, which is very slow for neutron stars. But it does imply that the star overall has a large-scale magnetic field that pokes through the surface. And we'll be using that critically further down in the talk. Here we go. I should also emphasize that I did all of the work here with a series of friends and colleagues at Columbia, and my student John Groger is responsible for the detailed data analysis that I'll show you. So, all right, so this you probably know, but I thought I'd stick it in if you don't. Neutron stars are the endpoints of the evolution of massive stars, right? Star does nuclear fusion of hydrogen to helium in the core. Once that starts to slow down because the hydrogen has been mostly converted, the core has to contract. Star still loses energy, can only get energy, conserve energy by contracting its core in its own gravitational field. The result of this is that the temperature in the core goes up, right? The virial theorem says that the temperature in the core goes up. And then once the temperature goes up and the density has gone up in the core, you start fusing heavier elements. So after hydrogen to helium, the next stable step is helium to carbon. And then from then on, you keep shooting alpha particles into the carbon, to oxygen, to neon, magnesium, silicon, sulfur, argon, calcium. Okay. So this goes on until the fuel is exhausted in a particular cycle. Then the star repeats the cycle. It again heats up the core, contracts the core, and you ignite the next cycle up. This goes on until you get to iron in the core. Iron is the most tightly bound nucleus, and you can do nothing to it that gives you energy. Anything you do to an iron nucleus costs energy, either fissioning or fusioning it. And so once iron starts to form in the core, the game is up, and gravity is king. And so since the star has no more accessible nuclear energy sources, the core has to collapse. Core collapses, supernova explosion, right? And then you get something that looks like this over here. Just prior to the collapse, this is the story that's in all the textbooks. The core will have some sort of a layered structure where in the very inner, hottest and densest pieces of the core over here is where you will find the iron. And it will be surrounded by layers of material that have undergone ever fewer nuclear burning cycles, right? So there'll be sulfur, silicon, argon, calcium, and all this other stuff over here, magnesium, and then the outer layers may be either oxygen or carbon or something like that. Neon will be in there. A fun fact to recite in talks like this and in classrooms always is that for a 15 solar mass star, the hydrogen burning takes about 10 million years. The helium burning goes on for 1 million years. The carbon burning goes on for 300 years. The oxygen burning goes on for less than a year. And the silicon burning takes 2 days. Okay, so between Monday and Wednesday, a core goes from silicon burning, and on Wednesday it implodes. So this is the result of an explosion. A lot of material, the entire outer envelope that's still hydrogen and helium is being blown out, of course. It also has trace elements of the elements that were already there when the star formed. It will also explode parts of this circumnuclear region, probably into interstellar space, so-called ejecta. And that's where ultimately all the enrichment of the interstellar medium comes from, right? So you probably know that everything in your body other than hydrogen actually came from a supernova explosion, right? So the explosion itself leaves either a neutron star or a black hole, probably depending on at least on the mass of the core that collapses and therefore the mass of the progenitor star. And then it may also just leave nothing, where the core completely disrupts and there's only a hole and nothing else. So this is Cas A, is a bright supernova remnant. This is an X-ray image also. And here again, I have to hold this. There's a neutron star in the middle of it. See that? Cas A is a supernova remnant that's probably 300 or 400 years old. Now I need this thing here, advance. All right, so I have 3 very simple slides that outline the basic properties of neutron stars that lead to an argument for why we believe neutron stars should have masses of order, I don't know, 1 solar mass plus or minus a solar mass, and why the radii of such objects should be in the range of a couple of kilometers. So if you believe and if you assume that the equilibrium in a neutron star is given by the force of gravity pushing inward, and the thing that resists this inward push is the fact that the material of the star is degenerate. The neutrons in the core cannot be coming closer to each other if they have the same momentum, right? There cannot be more than 1 neutron in any given quantum state. For a given momentum, that means that 2 neutrons cannot be very close to each other. Conversely, if you want to bring two neutrons very close to each other, you have to make sure they have very different momenta. Otherwise, they can't. So this is Pauli's exclusion principle. And the resulting degeneracy pressure is what counteracts the gravitational force. So now, in order to derive an expression for what the pressure of degenerate matter should be, we expect, because it's a purely quantum phenomenon, that the expression would contain some power of Planck's constant. It would probably depend on the mass of the neutron, and it should probably depend on the density of the particles, right? This is formally material at temperature 0, so the temperature does not occur, right? This looks very different from an ideal gas equation of state. So if I raise these numbers to powers alpha, beta, and gamma, and I say that the resulting expression must actually have the dimensions of pressure, right, for force per unit surface area, then I can work out that for alpha equals 2, beta equals -1, and gamma equals 5/3. On both sides, the dimensions are the same. There. So within a factor of a few, this is what the equation of state for fully degenerate gas of free neutrons should look like, right? M is the mass of the neutron, N is the density of particles, and h bar is Planck's constant divided by 2 pi. So now we have another equation that says that the gravitational force, right, over here, pushes in, and the gradient in the pressure opposes the gravitational force, right? Remember, it's not the pressure that holds the star up, it's the gradient in the pressure that holds the star up. So if I use the equation of hydrostatic equilibrium and I replace this by core pressure divided by the radius of the star, this is the density, the matter density. So this I replace by mass divided by the volume of the star. Acceleration of gravity, gm over r squared, right? Mass of the star divided by the radius of the star. Physicists usually start screaming at this point, like, you know, you got this differential equation, you're just going to replace it with an algebraic. Well, yeah, because it will only take 2 minutes, and the results are surprising. So this is the result of doing that to this equation. And now I'm going to set this equation equal to this one, right? So the pressure that opposes gravity is going to be provided by the degeneracy pressure. And in that case, you find that the radius depends on the mass of the star. As the radius goes, as the mass to the minus 1/3 power. So the more massive a neutron star is, the smaller it is. And then there's a bunch of physical constants over here, and this is a number of order unity, right? So the mass radius relation for a fully degenerate star in gravitational equilibrium with its own mass is the radius of the star is proportional to the mass to the minus 1/3. This is very different from ordinary stars, as most stars that are currently burning helium in their core have a mass radius relation where the radius of the star is proportional to the mass of the star. So if I substitute the neutron mass, gravitational constant, Planck's constant, if I substitute pi, I get that the radius for an object that has one solar mass in mass is 1.6 kilometers, right? So we expect stars of order, a solar mass, to have a radius of order a few kilometers, right? This is a very, very, very simplified calculation. It only assumes that the force that counteracts the gravitational force is the degeneracy pressure in a fully degenerate gas of free neutrons, which is already an idealization. But the mass radius relation must be sensitive to the details of this relation between the pressure and the density, which I abbreviated with that really simple calculation for fully degenerate gas of free neutrons. So we know that once the density is as high as it is in neutron stars, the neutrons are literally pushed up against each other. And in the core of the neutron star, it's possible that the neutrons literally get crushed. And they may dissolve into a gas of mesons or even a gas of free quarks. And currently, it's too difficult to calculate this kind of stuff from first principles. So people have been looking to experimental work to see if we can predict whether that's going to happen or not. And that's one of the reasons people think this is an important subject too. This is fundamental behavior of matter under extreme circumstances, and this is the best place to start looking for constraining those properties. Now, there must also be a maximum mass to a neutron star. So far I've not told you about the scale of the masses, but if you think about it for a little bit, you may remember that the derivative of the pressure with respect to the density in the equation of state is equal to the sound speed squared. And if the situation becomes so extreme that somewhere inside the star, probably near the core, the sound speed starts to exceed the speed of light, right? Then stuff must happen. So at that point, if I push harder on something, there is no way that the rest of the star can be told to adjust its density distribution because, you know, Frits is pushing over here. Gravity cannot be balanced by the degeneracy pressure because the sound speed, right, at which these adjustments are communicated, so to say, doesn't go fast enough to do it. So the core has to collapse. So anywhere within the star, sound speed exceeds the speed of light, you'll get collapse. So there must be a maximum mass that corresponds to the sound speed just teetering on the edge, just below the speed of light everywhere in the star. One way to understand this more physically, perhaps, is the following. You know, pressure is particles, right? If I hold up a little area, particles hitting this surface over here, they transport momentum across the surface. They transport momentum at a rate that's set by their velocity. And once the density gets really high and the energies get very high, these particles all reach the speed of light. And so the momentum transport saturates because the particles cannot move any faster than the speed of light. So while their individual momenta can still increase, the rate at which the particles cross the surface cannot increase. It's the speed of light. So once that starts to happen, that's when gravitational instability sets in. And you may be familiar with the case for fully degenerate gas of free electrons. That's called a white dwarf star, and in that case, the maximum mass is called the Chandrasekhar mass, and it's about 1.4 solar masses. For the fully degenerate neutron configuration, the limit is often referred to as the Tolman-Oppenheimer-Volkoff limit. It's that Oppenheimer, indeed. And it is, the simple estimate says that it should be about 0.7 solar masses, but the real limit with the real equation of state is thought to be somewhere near 2 solar masses, but we don't know precisely where it is. Okay, so from what I've just told you, we expect the neutron stars to have masses of order of solar mass, right? Maybe up to 2 or a little over solar masses, and radii correspondingly of order a couple of kilometers, so maybe 10 or maybe a little more. And that was all we knew for more than 50 years, really. So this is the first paper that was ever written on the theory of neutron stars, or actually the first paper that ever mentioned the possibility of neutron stars. And it's a paper by Lev Landau, and he published it in the Physikalische Zeitschrift der Sowjetunion, volume number 1, the first volume issued in Kharkov in 1932. I went to look for this. Princeton doesn't have it, NYU doesn't have it, Yale didn't have it, Columbia didn't have it, but the New York Public Library has it. So I went in there, and this is staggering, you guys. You imagine like a little room in 1932, these, New York Public Library employees is like, hey, Jim, there's a new theoretical physics journal in the Soviet Union. We should get a subscription to that. So there we go. So this is the first paper, and you may know that the next paper that Landau wrote on neutron stars was in 1938 while he was in jail, and it's the paper that got him out of jail. So why was he in jail? Because, right? People were arrested for no reason at all in 1938. Okay, so we're going to try to measure the masses and the radii of neutron stars, right? Now we pass into the realm of where astronomers usually take the first steps. And as you know, the first neutron stars to be found in nature were the radio pulsars in 1968. And so that's extremely important, very interesting stuff. But the somewhat disappointing aspect of radio pulsars is, for our present purposes, is that the radio emission has absolutely nothing to do with the surface properties of the neutron star. What you're seeing is radio emission that's generated in a relativistic magnetosphere through a process that's still not fully understood. And it doesn't tell us how big the star is or what its mass is. All you see is that the star spins, because you see the radio signal periodically vary, and you can see that it spins, and you can also see that it spins down very slowly. And so for measurements of period and the derivative of the period, you can actually estimate how fast the star loses energy. And if you assume that that's due to the fact that it is a big magnetized object that's spinning around and therefore loses electromagnetic energy, you can calculate the strength of the magnetic field. For most radio pulsars, you find that's 10 to the 12 Gauss, but there's outliers. And then since that time, so the reason that this might be really interesting is if you find the fastest spinning neutron star, it might tell you something about what the limit to the compactness of a star is, right? At some point, a star of a given mass and radius, if you spin it too fast, it will fly apart. So if you found a clear cutoff spin frequency, it might tell you something about the cohesiveness of neutron stars. So that's actually not worked yet so far. But in the meantime, people have found binary pulsars. So neutron stars, radio pulsars that are evidently in a binary, because you see the radio signal go beep 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 beep. So you can see that they're tracing out a binary. In a few exotic cases, in fact, there's 2 pulsars orbiting each other. Both of them have a periodic signal. So with that information, you can trace out the Doppler velocities, right? And you can say something about the properties of the binary. As you may know, if you've taken introductory astronomy, or if you think about this for the next 5 minutes, that information in itself is not sufficient to measure both the masses and the size of the binary, right? You need one more piece of information here. The velocities over here, the ratio of the 2 velocities is not, because you don't even know whether you're viewing the binary edge on or more tilted. That's one number you would never get out of this. Okay, now it turns out if the binary is close enough, there are general relativistic effects that affect the shape and the orientation of the orbit. And that you can actually see, because you see these radio signals change phase, and you can actually see that there's precession of the orbit going on. And you can also see that in the case of closed binaries, the binary is evidently losing energy because the binary is shrinking. And the binary loses energy because it emits gravitational waves, right? This is a half serious attempt to represent gravitational waves, right? So that doesn't clarify anything. But anyway, so you know that Hulse and Taylor, Joe Taylor, did this work for a pulsar called 1913 plus 16. And over the course of 25, 35 years, this basically represents the decay of the orbit, so to say, due to the emission of gravitational radiation. And in 1983, when did they get the prize for this? They got a Nobel Prize for this. Somewhere along this curve. Maybe at this point, the Nobel Committee did agree that there was just no other explanation for this. So it's a bit around there. Yeah. Okay. Even crazier, I thought I mentioned this, in some of these binaries, if they're oriented favorably, sort of edge on, you can actually see that the beep, 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 beep of the radio pulsar is actually delayed a little bit by the gravitational time delay as the pulse signal travels through the gravitational potential well of its companion, right? So that's called the Shapiro delay. And if you can see the Shapiro delay, that's just as good as seeing this change in orientation or decay of the orbit. You can actually get the parameters of the stars completely out of this. So if you see general relativistic effects of any kind, you can get the masses of the stars and the size of the orbit out of it. And so here's a picture of that Shapiro delay, right? So we're not talking about some marginal thing. This is a highly significant effect, right? You see that there's a microsecond delay in the arrival of the signal that goes up to 30 microseconds, and that comes back down again. And that's the fact that the signal travels through the gravitational potential well of the companion star. So from this, you can derive masses. Here's a number of masses plotted on this axis. Don't care about this mass for now. And you can see that this is 1.5 solar masses over here. You can see that these guys seem to sort of cluster around 1.5 solar masses, right? So you'll often hear say that the neutron stars have masses of 1.4 solar masses. It's not really true, but that's sort of where the average is. And then there's a number of them that actually have surprisingly high masses. The other thing that this graph doesn't show, but the next one does, is, no, it doesn't show this. Let's go to the next one, and then I'll go back, is that these masses are fantastically precise. Once you do get a handle on what the masses of the neutron stars are, you get a number out of it that's almost embarrassingly precise, if you see what I mean. So the best numbers here, the uncertainty on the mass is well under 1%, if I'm not mistaken. And so we go from a situation where we knew nothing to like knowing too much almost, right? It's 1.39 plus or minus 0.005 solar masses. What am I going to do with something that's so precise? So here's a number of different categories of neutron stars on a mass scale plotted over here. But I wanted to point out that some of those are very, very precise. You made one of the first versions of this diagram, did you not? Yes, and it has other objects in it too. Binaries with a non-neutron star. Okay, now the other thing you've heard about is that in 2017, in August, the gravitational wave detectors detected a signal that's undeniably the result of the coalescence of two neutron stars, a binary neutron star that lost energy to gravitational radiation, and then the two neutron stars crashed into each other. And you can see the signal over here, right? This is the LIGO and the Hanford and the Livingston LIGO detectors. As a function of time, 40 seconds over here, 30 seconds over here, you can see the frequency of the signal going up, right? So this is 40 hertz, and it shoots up just before the coalescence to 500 hertz. In principle, the gravitational wave shape, right? So you should imagine, because the frequency is 50 hertz, right? So 50 times per second. So this is basically a signal that goes till the frequency starts going up and up and up. So if you very, very carefully monitor that gravitational wave shape, it actually tells you something about the deformability of the neutron stars and the rate at which the frequency changes and the orientation of the orbit. And from that, you can determine the squishiness and the equation of state. That is, in principle, straightforward physics, but it is a somewhat messy calculation to have to do. So, okay, so now, if you wanted to see the surface of a neutron star, as I told you earlier, those things have radii of order 10 or 12, few to 10 or 12 or 15 kilometers or something like that. And if you take a neutron star with a radius of 10 kilometers and a surface temperature equal to the surface temperature of the sun, right, which you will probably agree is like pretty hot. and you put it at 500 parsecs away. A parsec is 3.1 times 10 to the 16 meters. It's a third of a light year. What is it, 3? A parsec is 3 light years. I got it wrong. Yeah, that's right. See, I always have to look this up because the newspapers always use light years, which we never use. So anyway, so sorry, 3 light years. So 500 parsecs is the size of the galaxy. The distance to the center of the galaxy from the sun is about 8,500 parsecs. So 500 parsecs is, a decent fraction of that distance, but that's sort of like, there's a couple of neutron stars closer by, but the typical distance scale that people talk about is a few hundred parsecs. So you take this star, you put it at 500 parsecs, and at that point, it's utterly invisible. So if you know how to read magnitudes, it would be 37.5 magnitude object. It's just currently not. What's our limit right now? JWST? In the red? 30. Yeah. Yeah. So actually, yeah. So this is still too faint to be seen, and that's the closest ones. So now, if you imagine raising the temperature of the neutron star to 1,000,000 degrees, remember, then the Stefan Boltzmann law says that the total luminosity of the star goes up to a very high number, and it goes as T to the power 4, right? So 6,000 to 1,000,000 degrees. So the luminosity increases tremendously. And the peak of the X-ray emission is going to shift into the soft X-ray band. So for 1,000,000 degrees, you would expect the peak of the spectrum, a black body spectrum to peak around 300 electron volts if you're more comfortable with electron volts. All right, so we're going to see if we can see neutron stars with X-ray observatories with these properties. And it turns out, yes, there is a variety of neutron stars that satisfy these requirements. So the first one I would mention are the so-called isolated neutron stars. And Martin and I did some work on this together. Martin was one of the first to do this. So people pointed X-ray telescopes at the sky, found a small class of mysteriously soft X-ray sources that had no counterparts, no stellar counterparts, and therefore were potentially very bright X-ray emitting neutron stars. And so these isolated neutron stars were looked at with the next generation of X-ray observatories. And here's a spectrum that was obtained with the Chandra X-ray Observatory between 20 and 80 angstroms. So 20 angstroms is about a half keV, so a half keV to 4 times less. And here's the spectrum displayed, and you can see a histogram, photons counted as a function of wavelength, and overlaid is a model, a dashed line. And this spectrum looks like a black body. And so more time was spent to see if you could see deviations from a black body, but those were not found to be significant. So the spectrum is an almost perfect black body with a surface temperature of 60 electron volts. And 60 electron volts is 6 times 10 to the 5 kelvins. So Martin and David Kaplan found that from studying small pulse variations and a change in the pulse periods, that the surface magnetic field strength of this thing is enormous. And therefore, the surface probably is composed pretty much entirely of hydrogen, and it's threaded by an incredibly strong magnetic field. And so these two things together somehow in this band makes stuff look sort of like a black body, which is, as you know, right? What is a black body? It's the spectrum of radiation in thermodynamic equilibrium. Thermodynamic equilibrium is the most boring state in nature, right? It only depends on temperature. It tells you nothing about the actual properties of the thing that produces the radiation. So this spectrum is nearly information free, if you see what I mean. It tells us almost nothing about neutron stars. So, but there's more of these objects, and some of them do show spectral features that probably have to do with the magnetic field, and we're still not quite sure how to interpret those. The other class of objects that are really bright in X-rays are neutron stars that are found in binaries, where the companion star feeds mass onto the neutron star, and that releases energy through the gravitational energy release, makes the matter really hot and becomes an X-ray source. And a small subclass of these objects, gas, accumulates on the surface of the neutron star. It's subject to unstable nuclear burning. And once in a while, every couple of hours typically, the whole surface will be undergoing unstable thermonuclear burning, and will briefly produce a flash of X-rays. The flash lasts 10 seconds, and then a few hours later, you get the same thing. So those flashes are bright enough that they outshine the light being released from the gravitational energy release. So then you're definitely looking at the surface of the neutron star. But the mass transfer that dumps the matter onto the star also transfers angular momentum, right? This is in a binary star. And so the neutron star, in the course of 1 billion years, is being spun up. And all the neutron stars in configurations like this that we know of, with one exception, spin at frequencies of several hundred hertz. And if you think of a 10-kilometer radius thing going around at several hundred hertz, you can convince yourself that the linear velocity associated with that at the equator is of order of a decent fraction of the speed of light. So any atomic absorption features in the spectrum would be washed out by the Doppler effect. And so these are not suitable objects either. There's only one object known to spin slowly enough at 11 hertz that it would be suitable for a study like this if you just take the bursts and then add several of those together and see what you can see. But that thing has been off since 2010. It doesn't produce X-rays right now. And then there's neutron stars that spin rapidly, and the emission on their surface is not uniformly spread around. So there are definable hotspots on the surface for a number of different reasons: very strong magnetic field, or because gas actually follows along the magnetic field falling onto the surface. But in any case, you can actually see from the X-ray light curve that they're actually rapidly varying. And there's a neutron star spinning, and there's 1 or 2 spots that produce most of that radiation. So now, if you knew that the spot was at the equator, for instance, right, then from the spin period itself, you could deduce the radius of the star. But because the Doppler effect would actually tell you what the linear velocity is, right, and the spin frequency, and then you know enough to deduce the radius of the circle. But of course, you don't know that the spot is on the equator. It's somewhere on this star, right? So people have looked at these things. The neutron stars spin. You can see them change in X-rays. You see spot coming by. And then you can model the light curves in different X-ray bands. And you can make assumptions for where the spots are located, et cetera, et cetera. And then you try to reproduce what you see. So this is sensitive to the radius of the star under the assumption that you know at what latitude the spots are located, but you can fit for that. And then the fact that there is self-lensing from the neutron star, right? Light emerging from the surface of the neutron star will actually be bent a little bit in the gravitational field of the neutron star. So you can actually see around the edge of a neutron star by a little bit. That effect is sufficient to give you sensitivity to the mass divided by the radius. And so in principle, very carefully studying these spots going around can tell you what the mass and the radius of a neutron star is. So here's an example. It's just a few years old. This is all work that's been done with data that's been gathered by a very nice small compact experiment called NICER, the Nuclear Interior Composition Explorer, I think. And so here's one particular object. There's an estimate for the radius of this thing of about 13 kilometers with uncertainty 30%, and a mass that's maybe 1.4 solar masses out here. Other people use the same data and come to similar conclusions. But you have to fit for a lot of parameters over here, right? This is not a simple thing of taking a graph, looking at one point, and then dividing by 2 pi, and you've got it. So the final thing I wanted to mention is young hot neutron stars. So when the core of a star collapses, the release of gravitational potential energy, you know where it goes, right? The core collapses entirely, and what does it turn into? Neutrinos. This is something that even astronomers sometimes forget. The core collapse of the core of a massive star, the protons and electrons form neutrons, which produces a neutrino. And pretty much all the binding energy that's being released as the star collapses comes out in the form of neutrinos. So looking out at the room, a lot of you were not around in 1987, in February of 1987, right? When a supernova exploded in a nearby dwarf galaxy, but some of us who are older than that remember it perhaps. That explosion was close enough that at the time of the implosion of the core, there was a flood of neutrinos released, and those neutrinos were seen in neutrino detectors on Earth. There's 19 neutrinos that were counted that would not have been seen under normal circumstances that can be traced back to this core collapse. And when I say core collapse, you probably you're thinking like, but it goes like this. There's a massive star. The core is now actually burning stuff to iron. It's out of fuel, right? And so what happens is the core collapse. This is like this piece of a star like this, right? But because there's so much matter involved in this, and it collapses to like a few kilometers, really, right? There's an enormous release of gravitational potential energy. So this comes out as a flush of neutrinos, and then it also drives out the rest of the stellar envelope, right? That's what you see right here in the supernova remnant. And the actual visual supernova, the visual light that you see in the course of like a year or so, that you can see it if it's not too far away, is only like of order of % of the total energy release. It's a total sideshow, but nevertheless. So Cas A was an explosion in the late 17th century. This is an image taken with the Chandra X-ray telescopes, and it's color-coded by element very roughly. So you can see that elements do get spewed out of this explosion and are not homogeneously mixed. Here's the neutron star. So this is the supernova that I want to talk about later. Here's the star that I will be discussing in some more detail. This is the Puppis A supernova remnant that I showed you earlier. And the neutron star is only a few thousand years old, so it's still hot from having undergone an implosion. So this is the Chandra X-ray observatory that we've used to do observations with. It's got an X-ray focusing optic over here that focuses X-rays between 0.3 and 10 keV or so. It has an angular resolution of about ½ arc-second. So that is comparable to what you would see from a very, very good photo taken with the terrestrial optical telescope, right? So when you see pictures of the starry sky with a really expensive, very nice telescope, Chandra makes similar images in X-rays. There's imaging spectroscopy with CCD detectors, and there's high-resolution spectroscopy of point sources with diffraction gratings that give resolving powers between 100 and a few thousand. And here is, I couldn't resist, but here is one of these instruments. This is a set of diffraction gratings, individual gratings lined up behind the focused X-ray beam out of the telescope. Each of these things looks on a small scale like this. There's 1,000 lines per millimeter, and all these little gratings have been oriented in the same way. So when focused X-ray light comes in, there's going to be a zero-order image right here, and there's going to be dispersed light running off in both directions, right? You know what a grating spectrum looks like. So thing works. This is a spectrum of the coronal line emission from a hot star. So between 12 and 24 angstroms over here. This is all emission from hot gas in the corona of the star Capella. And so now, what should you expect from a surface of a neutron star, right? So I turned the question slightly around. What can we actually see? And with the Chandra X-ray telescopes, for these few stars that are at the centers of supernova remnants, we would expect to see an absorption line spectrum. And if it has anything interesting in it, it would be due to oxygen and neon, because that's the band that we can cover, right? So carbon features are at lower energy, silicon and all the others are at higher energies. So if I take a model for a star that has a surface temperature of 3 million degrees, and I assume that the surface consists pretty much only of oxygen and neon, and I solve for the equation of radiative transfer in a gravitational field of 10 to the 14.6 centimeters per second squared, I get a spectrum that looks like this, right? So this is 6, 4, 2, 1, half keV, 5 to 20 angstroms. And you can see two spectra superimposed. This here is oxygen 8, hydrogen-like oxygen Lyman alpha. This is Lyman beta, Lyman gamma. The temperature and density are so high that most of the oxygen, if there's any bound, is in a hydrogen-like ionization state. And a similar series for neon. There's neon 10, Lyman alpha, Lyman beta, Lyman gamma, etc. And so what we expect to see, if we can see anything, would be the Lyman series of hydrogen-like oxygen and neon mostly. This is heavier silicon, and here's the spectrum is already declining, so it'd be harder to see that probably. So here's the same spectrum, and I wanted to draw your attention to, this is an absorption line, but you might wonder, this is an incredibly broad thing, and why is that, right? This is an absorption line that has like a 10% or so width. It's not like a sharp little Fraunhofer line, it's like a fuzzy thing like this. So this is due to the pressure broadening in the atmosphere due to the Stark effect. So the density in the stellar atmosphere is so enormous that the Stark effect produces a width that is this point over here. So this is a great opportunity, because if we can actually see these widths, we can actually measure the density and therefore the acceleration of gravity at the surface of the neutron star directly from the line width. This is an old spectroscopic technique that's being used in normal stellar spectroscopy, but here we would be applying it to neutron stars. And the Zeeman effect, by the way, should be comparable because we know what the magnetic field strength for this star is. In fact, we know that there's a field and we will take that into account. So the density in the photosphere, if you just take hydrostatic equilibrium and the gravitational acceleration is constant in the atmosphere, and you calculate what the density is at an optical depth into the atmosphere, that corresponds to equal probability for a photon to come straight out or be one more time scattered by an electron, then the density at that point, which is a characteristic point in the atmosphere, is of order 10 to the 24 particles per cubic centimeter, right? So you should all be going, ooh, that's almost solid density, right? It's enormous. And so at that point, the density is so high that the effect of the particles on individually radiating atoms becomes totally non-negligible, right? So that's pressure bonding. And so one way to think about this is the following. If you have a radiating atom, and if you think about the atom is like sitting there radiating, and then a particle comes by, an electron, and that's an electric field, right? That pulls on the bound electron as it passes by. That effect can be big enough to like change the internal structure of the atom that's radiating, and that will change the energies of the photons that are coming out. So one way to do this is to just say that the width of the line, the shift in energy that this produces is that your radiating atom can radiate and radiate till its wave train is being basically reset entirely by collision with an electron. It's going to radiate again till it gets another collision. So the mean time between collisions will set how many waves will be coherently emitted, and that will be the width, the relative width of the absorption process. And so you can calculate what that frequency is, right? The collision time, the mean time between collisions is the inverse of the electron density times the cross-section for collisions times the velocity of the particles. So this is how to do this yourself. So you don't have to ask other people. You can do this at home on a Sunday afternoon. So here's a simple recipe, but maybe we'll skip over it. How you can calculate what you need to do this calculation. You need a cross-section for the collisions, the strong collisions, right? And so there is a prescription that's due to Victor Weisskopf where he says like, okay, electron approaches, the frequency of the radiating atom is being shifted a little bit by the approach of the electric field of this electron. And then therefore the phase of the radiation is going to shift, and I'm going to integrate the phase shift up to the point that the phase shift is equal to unity. I'll call that a strong collision. That's how close an electron has to come. That distance is called the Weisskopf radius. And you can do that calculation. The Weisskopf radius ends up being this number over here. Depends on the velocity of the electrons over here. And the line width that this produces is directly proportional to how often electrons collide, which is proportional to the density of the electrons, inversely proportional to the density of the electrons, so inversely proportional to the temperature of the gas. And so this number over here for helium like oxygen, Z equals 8, under the conditions we've been talking about, 10 to the 24 per cubic centimeter, temperature of 3 million degrees, is 260 electron volts. This is huge, right? Because the transition, the Lyman alpha transition in oxygen 8 is at 653 electron volts. So this is almost a half of that number, right? That means that all these oscillations get to complete only 1 or 2 cycles before an electron cuts them short. All right. So now, in the spectrum that I've been showing you over here, this feature over here between Lyman alpha and Lyman beta in oxygen is by far the most prominent thing in the spectrum. And it shows for a wide range of effective temperatures and densities in the photosphere. This is always the biggest thing in the spectrum, right? And so this is a picture that shows we actually saw the spectrum in the spectral image. Here's the neutron star. You can see that there's dispersed light from the gratings over here. We took 400 kiloseconds of exposure with Chandra to get data on the star in Puppis A. That was delivered over the course of a year. I had to take all these images, align them, et cetera, et cetera. Ta-da. So this is what we found. Okay, so I got 6 minutes left, maybe. Okay. So this is the spectrum that we got, right? So this is a very faint object. You can see the noisiness of the spectrum binned up in bins of 1/10 of an angstrom, between 5 and 30 angstroms over here. And we just simply show the photons that we counted in the spectrum after we've subtracted the background underneath, right? So there's the brightness of the nebula, and the detector itself goes So that's been subtracted. And then that's all we did to it. So this sharp feature over here is nothing to do with the star. There's a huge absorption feature in the reflectivity of the mirrors, the X-ray mirrors. So that's what this is. So if I then take one of these model stellar atmosphere spectra, multiply them with the efficiency of the spectrometer and scale the numbers and then superimpose it on the measured spectrum, this is what I found. That's the red line over here, right? So that's one of those spectra that I showed you earlier, superimposed on the data. And this bump over here nicely coincides with that bump between oxygenated Lyman alpha and Lyman beta over here, which we said was going to be the strongest thing in any of the spectra. And then the neon features over here may also line up, but it's maybe less obvious right away. A typical error bar is of order this purple thing, right? A point with plus or minus a statistical uncertainty, and the uncertainty is just simply the counting statistics fluctuation from a Hamiltonian distribution. So this is a model that has a lot of oxygen, some neon, and it has a temperature of 3 million degrees. And I applied a gravitational redshift, which we haven't talked about yet, a gravitational redshift of it of 0.1, right? So that's what is needed to make the model spectrum shift on top of these things over here. So this constitutes, if it's correct, the first spectroscopic measurement of the gravitational redshift in a neutron star, which had not been seen before. But it's a somewhat small value. 0.1 is, if you work out with the acceleration of gravity that we've used over here, that's m over r squared, and the gravitational redshift is m divided by r. So you can solve for the mass and the radius of the star. If you do that, you find in this case for a redshift of 0.1 that the mass of the star should be a few tenths of a solar mass, and the radius would be maybe a few kilometers. So now you can do two things and say like, it is what it is. I've measured this, right? Or I can say like, maybe we should also look at other possibilities, because the firm expectation is that the neutron star should probably be more massive than just a few tenths of a solar mass. So then I put in the fact that we do know that the star has a magnetic field. So my colleagues measured the spin and the spin down of the star and estimate that the surface magnetic field strength is roughly a dipolar field, and the field strength is 3 × 10⁻⁻⁰ Gauss. 3 × 10⁻⁻⁰ Gauss. And that leads to a Zeeman split of 168 electron volts by itself out of 650 electron volts, right? So that's not negligible. Not only that, you also need the quadratic Zeeman effect, which is, the only time I've ever seen this was in retrospect. It didn't even catch my attention, was in my elementary quantum mechanics textbook. So the quadratic Zeeman effect comes about if you take the Hamiltonian for a particle in an external magnetic field, right? There's the momentum, here's the electrostatic potential associated with the nucleus. If there's an external magnetic field or electric field present, then you have to replace P by P minus Q over C times A in Gaussian units. And then you expand this and you get the old P squared over 2M kinetic energy contribution. You get a contribution that will represent, if you work it out, the simple Zeeman splits, right? The magnetic moment associated with the orbit of the electron interacting with the external magnetic field. And then there's the term in A squared, which always is crossed out because it's small. But in this case, it's not small. It turns out it's equally important compared to the linear Zeeman term. And because the effect is always to the blue, it turns out, because it's dependent on A squared, that means that the whole spectrum with the magnetic field present will be shifting towards higher energies. That means when I try to fit it to the neutron star, I have to shift it further to the red to make it coincide with the spectrum. And when I do that, I get this. So I get a model that looks very similar to the one I used before. That's because it is the same model, because I don't have anything else yet. But I did apply shifts for the quadratic Zeeman effect. And so these things over here now no longer coincide with oxygenate Lyman alpha, Lyman beta at a redshift of 0.1, but they coincide with oxygenate Lyman alpha and Lyman beta over here at a redshift of 0.28. Now we're looking at numbers that people are actually sort of maybe even a little too large. But nevertheless, if I take those numbers, I can unfold for an assumed, currently still only assumed, acceleration of gravity of 14.6. I would get a distribution of probability for the mass of the star in units of a solar mass that runs between, you know, 1.5 solar masses. The weighted average would be 1.6 solar masses. And the radius comes out to be 8.2 kilometers, but it could be as large as 10 or 12, 14 kilometers. But this is not final yet because this colloquium was too early. So it does depend on us developing a precise model for the shape of those absorption lines in the presence of a magnetic field, which is being worked on, but it's not final yet. Ready for your questions?